Greetings, chemistry students. Today I just want to go through a little bit more with some stoichiometry, some review, some refresh, a little bit of reteaching of this. So, just a refresher that the term stoichiometry means using coefficients in a balanced chemical equation as a mole ratio. So, the key thing is that coefficients provide us with the ratios in terms of moles. So if we look at this chemical equation here, 2 KCl's plus 3 O2's makes 2 KClO3's. What this means is that when 2 moles of KCl react with 3 moles of oxygen, they produce 2 moles of KClO3. So one way to do this that I think can help you keep from getting too terribly confused is we're starting in this problem. It says if 5 moles of KCl react. So we start with our 5 moles of KCl. And we need to essentially switch compounds between moles of KCl and moles of oxygen. Now, for every 2 KCl's, there's 3 oxygens. But to help us keep everything straight, if we just set up a little conversion where we take what we're starting with, which is KCl, and put that on the bottom, and we put what we're trying to find, which is moles of oxygen, on top, then we just go up to the equation, and since there was a 2 in front of the KCl, we put a 2. Since there's a 3 in front of the oxygen, we put a 3. And so what we're looking at is essentially what is 3 halves of 5. And 3 halves of 5 is going to be 7.5 moles of oxygen. Right? If we have a problem where instead of us starting with moles, we're starting with grams of something, then this involves a little bit more math that we're going to have to do. So if we're starting with 17 moles of oxygen, and we're trying to get to grams of KClO3, well, our first step is, well, since we're in moles, we can just go directly up to this reaction and set up a little mole ratio. So for every 3 moles of oxygen, we make 2 moles of KClO3 because 3 oxygens, 2 potassium chlorates. And so if we find what 2/3 of 17 is, then that's 11.3 moles of KClO3. And then if the problem wants us to get that into grams, we just need to multiply that by the molar mass of potassium chlorate. So we take the mass of potassium, which is 39.1, plus chlorine, 35.45, plus oxygen, which is 16 times 3. Because there's 3 oxygens, so we multiply this by 122.55, and we get a really big number, 1,388.5 grams, right? And so that is ultimately how you solve this problem. If you want to kind of look at what we're doing to solve this problem, essentially, we have our little mole town where we've got particles, liters, and grams. We've got the different things. And then we have whatever substance we're trying to find, which is typically a substance B in our reaction. We'll call it substance B. And it's got its own little mole town over here. Well, the coefficients in the balanced equation are essentially that bridge that lets us change compounds. Because over here, You divide by these things going into moles, you multiply them going out of moles. But then when you need to switch compounds, that's when we're using these coefficients as mole ratios from our balanced chemical equation. So let's look at another example. So this says if 1 mole of C4H10 reacts, how many moles of CO2 are produced? So if we have 1 mole of C4H10 and we want to find moles of CO2, so we want to switch compounds. We want to go from moles of C4H10 to moles of CO2. We take what we're starting with, goes in the bottom. What we're trying to find goes on the top of our little fraction here. And then we take our coefficients. C4H10 has a 2 in front of it. CO2 has an 8 in front of it. So we need 8/2 of 1, which is 4 moles of CO2. In other words, if you look at this equation, for every 2 moles of C4H10, we make 8 moles of CO2. So if we're only using 1 mole of C4H10, we'd get, or half as much, we'd get half as much CO2. So now let's look at the most complicated type of problem I could ask you, where we're starting not in moles, we're starting with molecules, and we're trying to find something that's not in moles. We're trying to find liters. So if we look essentially at this roadmap, we're going from particles to moles in the first part. So we're going to have to divide by Avogadro's number. Then we're going to have to use our mole ratio with our coefficients. And then, since we're trying to find liters, we would use the 22.4 liters in a mole. So for this one, our first step is to get these 5.7 times 10 to the 24th molecules into moles. So we need to divide by Avogadro's number. And when we do that, we come up with 9.47 moles of oxygen. Now that we've found moles of oxygen, we can go up to our equation and use our mole ratios that for every 13 oxygens, we get 8 carbon dioxides. So for every 13 moles of O2, we get 8 moles of CO2. And we set this up so that whatever we start with moves to the bottom so that those units would cancel. So this will give us 5.83 moles of CO2. And then the last step is that we need to get those moles into liters. And just like we've already learned, to get moles into liters, you just multiply it by 22.4 and you get 130.54 liters of carbon dioxide. So I hope that's helpful to you in solving some of these problems. If you're still having some trouble, reach out to me. I'll be happy to help you out through a Google Meet or through some in person tutoring, whatever it takes to help you with this. And with that said, y'all have a great day.